So what we talked about on yesterday, was really identifying the transformations of a function. And we talked about it as g of x equals a parentheses b of x. Yes, sir. I do not. I think a few took note sheets on Friday, and then between then and today, they've lost them and then got an extra one, so then the extras are gone. Because I normally print the exact number that I need. So if anybody grabs an extra one that already had one, someone else loses it. But they are all, well, they'll be posted up here. So you can rewatch the video and get them. Now, what we talked about yesterday with the function, this here, and really I wrote it as a parentheses bx minus h squared plus k, looking at the overall function. So we're not going to worry too much about it. But what we are going to be doing is actually looking at the transformations. And we're going to go back to the transformations that we had in 1.3 and the forms that they showed up in there. So the y equals f of x plus k was the transformation we were looking at when it moved up or down. F of x minus h is our left or right. Our y equals a f of x was our vertical stretch or shrink. Our y equals f times of a of x is our horizontal stretch or shrink. And our last two is y equals negative f of x is our reflection. Across the x-axis. And our last one, y equals f of negative x is our reflection. Across the y-axis. And these are all the ones we had from 1.3 when we really were talking about the overall transformations. Now this is different than what the book will show you, because if you look at the book, and it does do some of the example problems that we do in class already worked out there, they're going to do it differently. Because they're going to apply the spots where the transformations occur. So if we have a reflection across the x and a vertical stretch, they're going to plug that number in for where a occurs. And if we have up 3, well, they're going to plug the plus 3 in for k, and that's our function. But I don't like that. So let's put the Chromebooks away. You don't have to shut them, but just out of the way. Because if we think back to 1.3, when we actually did the movements, because I showed you one example where we had a vertical stretch and then a translation up. And then I did it the other way, where I did the vertical translation up and then applied the stretch. And did you notice, because when we noticed that the vertical movement up changed, because the vertical stretch and the vertical shrink affected our movement up or movement down. We saw the same thing with our horizontal stretch and shrink and the horizontal translation. They affect each other in the order in which they occur. So plugging them in, and like the book will show us, does work just fine because of the order in which the transformations occur. And throughout most of the example problems we'll look at today, they could plug them right in and it'd work. But if we had it in a different order, it would change what they look like. Because if we take the movements up, down, left, or right before we take a vertical stretch or shrink or horizontal stretch or shrink respectively, it'll change it. And the goal of what they're looking at in this section is really, can you see where is the reflection for x, reflection of y? Where is that going to be located? Where's the horizontal stretch or shrinks value going to be located? Where's the vertical stretch or shrinks value going to be located? Where's the movement left or right or up or down? Where is that located in the general form of the function? Which we can do, but why do that and then when you actually come back and applying the function and need to know the correct order, have to re-go back over it and relearn it because of how the order matters? I don't see the point in that. That's why I have to relearn something because you learned about it in a special way in one occurrence. So this here, utilizing these will work every single time no matter the order. Plugging them in works as long as the order doesn't affect it. As long as the horizontal stretch or shrink, or the vertical stretch or shrink goes first before the up or down. Or as long as the movement left or right occurs before the horizontal stretch or shrink. Because if they're in that order, then it's fine. But if they're in a different order, it will change how they work. Now, the only other thing we have is the vertex, is h comma k, and we'll be identifying it here. We'll go more in depth in it tomorrow. Now, the vertex of the function is the lowest or highest point. Is the lowest or highest point of the graph. And it's going to be h comma k. Now, we're going to look at the first example of the day, this one right here. Now, there are a few transformations. Let G be the graph, or let the graph of G be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the graph f of x equals x squared. Write a rule for G and identify the vertex. So when it says write the rule, really what it's saying is we're just applying the transformations. We're just going to apply the transformations. Now, what is the first transformation that's listed? Vertical stretch by a factor of 2. Now, the vertical stretch one is y equals a times f of x, because that's vertical stretch or shrink, y equals a times f of x. And that'll be the first one that we use. Well, our value of a, the stretch is 2. Because vertical stretch or shrink, it's exactly what we think it's going to be. Since they delta stretch of 2, we plug in 2. Now, what is f of x? X squared. So we'll replace f of x with x squared. Well, this is just 2x squared. Almost, because we still have 2 other translations or transformations to do. Because we did the first one, we have 2 left. Now the next one was a reflection in the x-axis. So y equals negative f of x. Well, we don't have f of x anymore. We have h of x. We just called it h of x because we needed another definition for it on the partway through. Well, what is h of x? 2x squared. So I can multiply everything inside the parentheses by the negative, which just gives us negative 2x squared. Well, we need to call it something else, yes? Well, someone give me a letter. J. Okay, so j of x. We'll call it j of x. Because it really doesn't matter. It's just we're getting to g of x, so we'll call this one j of x. Because we did the vertical stretch and the reflection, what are we missing? 3 units down. Well, that'd be our y equals f of x plus k. Well, we don't have f of x anymore. We have j of x. And how far are we moving it? So that would be minus 3. Well, j of x is negative 2x squared. We have minus 3. Well, that's just negative 2x squared minus 3. And that there would be g of x. So this one here, it worked out that they set it up in such a way we really could have plugged the numbers in. Because we know that the a, the number in front of the parentheses, is our vertical stretch or shrink, so we know it would be 2. Since it is a reflection in the x-axis, it would really be negative 2. We throw it in for a. The k value is our up or down, so we could have thrown that in as negative 3. So I'm going to erase this here for a second, and I'll put it back up. Because really what they're saying, and what the book will show, is they're going to take this here. Well, they say A is our vertical stretch or shrink and the reflection in the x-axis. So since it's a factor of 2, we would say 2 for A. And it'd be negative because it's a reflection in the x-axis. That's where that takes place. X minus, did we move it left or right? Well, no, so it'd be 0. And then we moved it down 3, so negative 2x squared minus 3 is how this would work, is what they would say and suggest. But I'm going to erase that. Now, if I started from the translation of 3, I'm going to go in the backwards order, because this will make the point kind of clear of why this works better to do it in the way we did it. Because if I start with this here, well, that'd be f of x minus 3 units down. Well, f of x is x squared minus 3. So h of x would be x squared minus 3. Well, that hasn't changed anything yet. Reflection in the x-axis. Well, that would be our negative h of x as we just saw. Well, that'd be negative x squared minus 3. I have to distribute the negative, which would be negative x squared. Well, the negative and negative 3 would make it plus 3. Well, that's already changed it a little bit, yes, because the one we had originally was minus 3. But we're not quite done yet. We still have a vertical stretch of 2. So we can call this j of x still. So we'd have 2 times j of x. Well, that'd be 2 times negative x squared plus 3. Distribute that. Well, that'd be negative 2x squared plus 6. Well, I can't just plug it in if I'm doing it in a different order. So some orders it works out that we could just do that plug in and get the function. But if we do it in a different order or affect it in a different way, it doesn't quite work the exact same. So that's why I was showing you the way that I did, because I want you to be able to have the flexibility to do it in any order, not in these specific set ways. So, on and back up. Now, the last thing we have is what they talk about or call the vertex. Now, the vertex is h comma k. Do we have an h value? Well, h is where? Inside the parentheses, being either added or subtracted from our x value, yes? Do we have a value in parentheses being added or subtracted from x? No. So what is the only number that we could add or subtract from another number and not change anything? 0. So h is 0. Now what's our k value? Almost negative 3, because we went down 3. So the vertex is 0, negative 3. Now the vertex for the actual graph, or the original function x squared, its parent function, is 0, 0. Because when we looked at all the graphs yesterday, it hit the origin, it hit 0, 0. That is the vertex, the lowest point x squared is. So that's where it would start out. Now for this here, did we move the function left or right? Well, no. So the x value would still be 0. We didn't change it But we did do what? It moved it down. So the vertex went from 0, 0 to 0, negative 3. That's it. It tells us where the lowest point is. Questions on this? Let's look at the next one. Let the graph of G be a vertical shrink by a factor of 1/2, followed by translation 2 units up of the graph of f of x equals x squared. Write a rule and identify the vertex. Well, our first transformation is what? A vertical shrink of 1/2. So we're dealing with y equals a times f of x. Well, what is our value of a? 1/2. Well, what is f of x? X squared. So this is really just 1/2 x squared. That's first step. First translation done. The second one is a translation of 2 units up. So y equals f of x plus k. Well, we really don't have x of x anymore. We have h of x. And our k would be plus 2. Up 2 would be a positive 2. What is h of x? 1/2 x squared plus 2. And that there really would be it. I mean, we could put parentheses around the 1/2 x squared, but then we would just drop them and get 1/2 x squared. We're not really applying anything to it. Vertex is our h comma k. Well, do we have an h value again? Because h value is inside parentheses and added or subtracted from x. But we don't have any parentheses, so our h is still 0. And k would be 2. Any questions on this here? You feel good about this? Yes? And as y'all can see in the notes, this is the last one of the day. Let the graph G be a horizontal shrink by a factor of 1/3, and a reflection in the y-axis, followed by a translation 2 units up of the graph f of x equals x squared. Well, our first movement is a horizontal shrink. Well, horizontal stretch or shrink is our y equals f of a of x. Y equals f of a times x. Now they said it's a horizontal shrink by a factor of 1/3. Almost. Since it's horizontal, we have to flip it, so it's 3x. Yep, inside those parentheses, we got to make sure it's kind of that opposite of what we think. So 1/3, instead of plugging 1/3, we plug in 3. Now our actual function of f of x equals, do we have f of x anymore? We have 3x instead of x, yes? So that means this x squared wouldn't be x squared anymore. It's going to be 3x squared. Yes. Now we could leave it like this here. There's nothing wrong with leaving it as 3x squared. Now, because there's nothing added or subtracted to the x, so having something like 3x minus 1 squared, we can simplify this. Because really, if I wanted to simplify 3x minus 1 squared, anything that's being squared is being multiplied by its. So really, we would have 3x minus 1 times 3x minus 1. Now, I would simplify this if we're actually solving for a value. If we're trying to find the value of x that makes the function equal 0, then we'll need to simplify it. But if I just had 3x minus 1 squared, I'd leave it alone. Because again, that minus 1 is our value of h. It's telling us part of the vertex. But here, since we just have 3x squared, we could actually write it as 3 squared is 9x squared. So I'm going to keep working through this. I will rewrite the 9x squared and the transformations for it down below. But there's nothing wrong with leaving it as 3x in parentheses squared. Let's see what's next. So we did that in a reflection in the y-axis. Well, this is our y equals f of negative x. Again, I'm just going to stick with h of x because that's what we've been using. So really what this is saying is that y equals h of negative x. So here we're replacing in h of x with negative x because we replaced the h of x is x with negative x. So I need to replace it in every part else. So that would be 3 parentheses negative x, close parentheses, squared. Well, what is 3 times negative x? Well, negative 3x. Any questions on this here? Now, if we were to apply this with the 9x squared, it would still work, but we would have 9 negative x squared. Well, we could simplify negative x squared because negative x times negative x is just x squared. Now we're almost done. Because I know the last one is a translation 2 units. So our last ones are f of x plus k. Why not? Let's stick with j of x. So really we have y equals j of x plus 2, since we're moving it 2 units up. Well, our j of x is negative 3x squared plus 2. So we'd have negative 3x squared, or really parentheses, negative 3x, close parentheses, squared, plus 2. Now, what would the vertex be? I would agree with the 2. 0. But again, when we look at the general form, that bx minus h inside the parentheses, the h is always going to be added or subtracted inside the parentheses from x. The b gives us a horizontal stretch or shrink. It doesn't tell us the x value, or the x value of the vertex. Are there questions on this here? Now, this last part really, if we use the other function, is just going to end up being 9x squared plus 2. Because if we multiplied it out, Let's see here. Let's see here. This one. So I went on and graphed it for y'all because I did it in Desmos and they graphs for us. Now the bigger one here, if I can write, this here is just our x squared. The smaller one here is our negative 3x squared plus 2. Now what I can do also is this one here, 9x squared plus 2, the other function that we had. It's very slight, but if you look at the one inside, can y'all see how it's changing colors? Because it's the exact same function. It does describe the same function. So it gives us the exact same thing. And it's really, the reason it doesn't look different is because since it's still lined up on the y-axis, the reflection across the y-axis is just putting it back onto itself. It doesn't change the overall function. If it was off the y-axis, then it would be a little bit different. But that is it for today. That is all we're doing. Yes. So your homework is on page 66. Problems 3 through 11 odd, 17 through 21 odd, and 27 through 29.